En esta ocasión tenemos la contribución del máster Crispin Logan, quien tiene una maestría en física y matemáticas, estudió en la Universidad de Durham, en Inglaterra. Actualmente es investigador del Observatorio Astronómico. Crispin nos va a dar una charla ligado al uso de los rayos X, los datos de los rayos X para estudiar objetos compactos y los procesos que tienen lugar en ellos.
Thank you to Dr. Lopez for the introduction, and thank you to you for coming and for your presence today. Talking about a real-life example of using X-ray data to find more about ultraluminous X-ray sources. Okay, so as I said, starting very simply, what are X-rays? X-rays are electromagnetic radiation. So we can think of them as a wave. We have the electric field oscillating here, the magnetic field oscillating here, perpendicular to each other, and the direction of propagation of the wave is perpendicular to both the electric field and the magnetic field. Each X-ray photon has 1,000 times more energy than an optical photon. Why is this? This is because the wavelength, lambda, is much smaller in an X-ray than in optical light. We can see here, this is the wavelength of an X-ray, 0.1 to 10 nanometers, whereas with optical light, it is in the range of 400 to 700 nanometers. So the wavelength is about 1,000 times smaller. And using this formula here, which gives us the energy of each photon, it is proportional to the inverse of the wavelength. So the energy of each X-ray photon is around 1,000 times more energetic than an optical photon. We generally treat X-rays as photons, not as waves, because they are in the high energy range. They're measured in units of electron volts, so 1 electron volt is 1.6 times 10 to the minus 19 joules. And X-rays are found in the energy range of 0.1 to 100 kiloelectron volts. And their wavelengths, as I mentioned before, are between 0.01 and 10 nanometers. X-rays have enough energy to penetrate material, which brings us on to the next slide, which is how much material can an X-ray penetrate. Okay? So this depends on two things. It depends on the atomic number of the material Z, the amount of protons in the nucleus of each atom of the material, and the energy of the X-ray itself. The higher energy the X-ray has, the further it can penetrate into a material, and the higher proton number, the higher the Z of the material, the less is the penetration distance. 10 centimeters of air at atmospheric pressure will stop 90% of 3 kiloelectron volt X-rays. As we can see here, cosmic X-ray sources are most clearly detected in this energy range. So a 3 kiloelectron volt X-ray is a typical X-ray from space. So from this it should be clear that if we have an X-ray detector here on the Earth, the atmosphere will absorb all of the X-rays, so we need to go above the atmosphere to be able to detect X-rays and collect X-ray data. Here are 3 different X-rays. 30 kiloelectron volt X-rays, we have to be above 35 kilometers of the atmosphere. For 3 kiloelectron volt X-rays, we have to be above 80 kilometers of the atmosphere. And for 1 kiloelectron volt X-rays, we have to be above 200 kilometers of the atmosphere. Typical cosmic X-rays, as I said, are in this range. So we really have to be above 80 or 200 kilometers worth of the atmosphere. This is why X-ray observatories now are predominantly satellites. This is for two reasons, because they can be above all of the atmosphere, whereas rockets and balloons often do not go above all of the atmosphere, they only go above a certain part of the atmosphere. And secondly, the balloon and the rocket have to come back down to Earth, whereas a satellite is continuously above the atmosphere, so the observations that we can take can be of any duration we want. This graph here shows the wavelength of light, and this is atmospheric opacity. So when it is 100%, this means no electromagnetic waves of these wavelengths can penetrate the atmosphere. So we see in this range here, where X-rays are, the opacity is 100%, which is why we need to be observing from satellites, so we are above 100% of the atmosphere. We can see here there is a window. This is the radio wave wavelength and the visible light wavelength here. This is why we can have ground-based observatories for radio waves and for optical light, because these waves can penetrate the atmosphere. But with X-rays, they do not penetrate the atmosphere, so we need to take observations from above the atmosphere, from satellites. The two main X-ray observatories that we have now were launched in 1999, both of them at a cost of hundreds of millions of dollars. One of them is XMM here. So the cameras have a collecting area of 0.4 meters squared, whereas in Chandra, the other X-ray observatory, the cameras have a collecting area of 0.1 meters squared. So in terms of sensitivity, XMM has a higher sensitivity because the collecting area is 4 times as large. So for example, if we are looking at a very far away galaxy, which does not emit very many photons, we would probably use XMM. So why then have Chandra? The point spread function of XMM is 15 arc seconds, and for Chandra, it is 0.5 arc seconds. So it has a much better spatial resolution. So why would we use Chandra and not XMM? For example, if we are looking at a close galaxy, for example, Cygnus A star, the closest powerful radio galaxy, we could use Chandra, because within the galaxy, given the small point spread function of 0.5 arc seconds, we will be able to see detail within the image of this galaxy that we could not see with XMM with the much higher point spread function. So these two observatories are very complementary to each other. And finally, they both have a similar energy range. This is the energy range where the majority of cosmic X-rays are found. There are other observatories that observe up to a much higher limit. For example, there is a new-ish satellite called NuSTAR, which measures X-rays up to 79 kiloelectron volts, but fewer X-rays are seen in this higher energy range. So these two satellites focus on the energy range where most cosmic X-rays are seen. Okay, so cosmic X-ray production. How are X-rays produced in space? We have black body radiation from star-like objects. So this is treating a star or a star-like object, it could be a black hole or a neutron star, as a black body, and the spectrum we see from this looks like this. So the spectrum we have on the x-axis, photon energy increasing, and relative intensity increasing. Relative intensity can also be measured as counts per second or photons per second, arriving at the camera within a certain energy range here. This is the black body curve for a black body of 2 times 10 to the 6 Kelvin. As the temperature increases, the curve will change. Also, if we change the direction of or accelerate a relativistic electron, so an electron that is already moving at a significant fraction of the speed of light, if this changes direction or is accelerated, then X-rays are released and produced, rather, and it will give a spectrum that looks like this here. This is called a power law spectrum. And finally, another way that X-rays are produced in space is by thermal emission from a hot gas. So if the hot gas is above 1 million Kelvin, then it will be split into protons and electrons. And if an electron passes a proton, it will be accelerated. It will change direction, and this will emit electromagnetic radiation in the form of X-rays. And the spectra we see from this looks like this, and it is called thermal bremsstrahlung. And bremsstrahlung is a German word meaning breaking radiation, because the electron is breaking as it goes around the proton. Okay, so now on to the next part. I will give an overview of compact objects, what they are, and why we use X-ray astronomy to study them. So compact objects are very dense objects. They are objects of a very high mass in a very small volume. Some examples are a white dwarf, which has a mass of 1.4 times the Sun on average, and the radius is 5,000 kilometers. So it's about the size of the Earth, but it has the mass of the Sun enclosed within this volume, so it's very, very dense. Denser still, we have a neutron star with a mass of 1 to 3 solar masses within a radius of 10 kilometers. So this is denser still than a white dwarf. We also have black holes, which can have a mass from 5 solar masses upwards. And just so you can get an idea of the density of a neutron star, 1 teaspoon or 5 milliliters of a neutron star would have the same mass as 5,000 million normal family hatchbacks here. Okay? And this is why it's really interesting to study these compact objects. On Earth, there is no laboratory where we can replicate the gravitational forces around a neutron star. We cannot have this much mass in a small volume, or we just cannot have this much mass, obviously, because the mass of a neutron star is much greater than that of the Earth. So we can test the laws of physics in extreme environments and different regimes that we cannot replicate in a laboratory here on Earth. So this is one reason to study compact objects and what happens around a compact object. So how do these compact objects form? We can see here the white dwarf, neutron star, and black hole that were mentioned on the previous slide. We'll start from the beginning. So this is in the birth of a star. We have a stellar nebula, which is a big cloud of gas and dust, and within this cloud there are random density fluctuations. So one part will be denser than another part and will attract matter towards it. This process keeps going, and it will release heat as it happens, because gravitational potential energy is released as the matter falls towards the denser region. The pressure, the temperature, and the density increases until fusion can start. Nuclear fusion starts, and then we create a star. So this is where a star spends most of its time, undergoing nuclear fusion. Depending on the star, it could be tens of millions of years to thousands of millions of years. Towards the end of the lifetime of a star, it starts to expand. Depending on the mass of a star, it will be a red giant or a red supergiant. This phase is relatively short-lived compared to this stage here. And then finally, in the case of a massive star here, the fusion in the center of the star stops, so there is no force pushing the matter outwards. There is only the gravitational force inwards, so the star collapses to form either a neutron star or a black hole. If the infalling mass is so great that it keeps falling in, we create a black hole. However, if the mass is less than a certain amount, we create a neutron star, because the huge mass of the star is compacted into a tiny space, and it does not want to be compacted any further due to the Pauli exclusion principle, so it will stay as a neutron star. But when there is mass above a certain limit, it will keep on contracting until a singularity, which we define as a black hole. And then the power law, which is from changing the direction or accelerating electrons. So this is when material is accreted on and falls onto the black hole. The electrons are accelerated, creating X-rays. So in any spectra of this system, we expect to see a black body radiation curve and this power law. Okay, so what was the aim of the project that I did studying these ULX systems? I wanted to find out if there were any coarse changes in the spectra and the associated physical parameters as luminosity changes around the Eddington limit, so just below and just above the Eddington limit, for accretion onto a stellar mass black hole. If there is a change in spectra between the sub-Eddington and the super-Eddington state, this will suggest a change in the physical accretion state. So we need to look for a change in spectra. I used a previously prepared catalogue of these sources from a paper from Gladstone et al. Written in 2009, together with some other data for sources with luminosities below the ULX limit, to be sure that we are looking at systems that are accreting sub-Eddington, below the Eddington limit as well. So to start, I sorted the sources into two luminosity bands using certain criteria. I took sources within a certain distance from us and with a total count above a certain amount. It was 2,000 counts, such that I chose the highest data quality. I had 40 to 50 sources in each band, which is enough to make statistically significant conclusions from the analysis of the data. The luminosity bands that I chose were, remember this is the 1 times 10 to the 39 ergs per second, is sources above this are defined as ULXs. So I chose the band below this and a band above this. I modelled the sources, the data from the sources, with different models using XSpec. So XSpec is a program that takes the X-ray data collected from the satellite and models it. You can choose the model and you can see how well the data fits the model. So the three models that I used were the power law model, the black body model, and then a two-component model, so these two components together. Why did we use these models? So I was only looking for simple changes in the spectra, so therefore I could use simple models. It turned out that actually these results were unnecessary. It was unnecessary to use a two-component model because often the power law model or just the black body model would fit the data well enough that the extra component was unnecessary and gave us strange values. So this was the case in a lot of the observations, so we discounted and we did not look at these two models together. We ended up only looking at the power law model and the black body model results. We also used the power law and the black body because a paper by Sutton et al. 2013 classified the spectra of sources around this ULX limit into 3 different spectra. So you can see here, this is just the disk black body, and then these 2 are the 2-component model, where you have the black body spectra and also the power law component. So this is why we chose the power law and the black body model as our 2 models. So you model the data against the power law, and we have 3 different parameters as the output. We have the column density, the photon index, which is just the gradient of the power law, and the null hypothesis probability, which tells us how well the data fits the model. For the disk black body model, again, column density, null hypothesis probability, and also the inner disk temperature. So this is this here. The curve will look different for a different inner disk temperature. This is an example spectra. These dots here, these are the X-ray data taken from the observatory. And these lines here, this is the model fitting the data. We have 3 different lines because there are 3 cameras taking observations at the same time. This chi-squared significance, if it is 0, this means that the model fits the data well. So we can see here, it is 20, and this means that the data does not fit the model well. So why is this? Around 1 kilo-electron-volt, this is because there is gas flaring in the local environment to the X-ray observatory taking the data. And this high chi-squared significance, this appeared in various observations. So various observations were contaminated, so we had to clean these observations. We clean them by looking at the light curve of the observation. So the light curve gives us the rate in counts per second, and this is the time. So this is just as the observation goes on. We can see that around 10 kiloseconds, there is a big flare. So what we needed to do is only look at this part of the observation. So there is a program where you can extract just this part of the observation, so we do not have this contamination. You can also find the source, which in this case is here. This is the background area, and you extract these 2 regions from the observation, and you extract the background from the source, so we are only then seeing X-ray data from the source itself, and we do not have any background contamination. So what we did with these 40 to 50 sources in each band, we modeled them against the power law model and the black body model, and these are the results that I got. So this is for this top one is the black body model. You can see that in the low luminosity band, the NH value does not change. Within standard error here, the column density does not change. This is also true for the inner disk temperature. And in the power law model, the same is true. To within standard error, the values do not change. And this is also true for the photon index. The values do not change within standard error. However, comparing the averages obviously is not a very thorough analysis of the results that we got. So the next step I did was compare the distributions of the values. I did it for the power law and the disk black body model. And these are the results. These are histograms for the disk black body model. Here we have the number of sources, and here we have the inner disk temperature. The red line is the average value, so we can see the average is very similar, 1.13 here and 1.17 here. So within standard error, they were the same. However, we can see that the distribution is very, very different. Here, it is centered here. However, this is much more spread out. So this suggests to us that there is a change in the sub-Eddington and the super-Eddington accretion states. However, we want to quantify this and prove this more than just looking visually at two histograms. So we can do this, we can compare two populations, two groups, and see if they are different using the Kolmogorov-Smirnov test, or the KS test. So the KS test gives us a value, p, between 0 and 1. If the p value is small, it means the two populations are different. It means that there is a different accretion state, or a difference in the spectra, between the two luminosity bands, the low and the high luminosity band. These are the results that we got. So we compared all of the parameters that we get from the model. Interestingly, it was the inner disk temperature that gave us a low p-value, which tells us with quite a strong probability that there is a difference in the accretion state and therefore the spectra between these two luminosity bands. Something else that was serendipitous, so just lucky, is that I had recurrent sources in both bands. So the same system in a different observation appeared in the low luminosity band and the high luminosity band. The advantage of this is that we know the black hole mass in the low luminosity band and the high luminosity band is going to be the same. So the only thing changing is going to be the accretion, the level of accretion onto the black hole. So we compared these two recurrent sources between the low and the high luminosity band. So this is source A in the low band and the high band. There is no change for the power law model of the column density. The photon index also, there is no change within the standard error. Interestingly, for the disk black body model for this source, the column density within standard error, there is a big change between the low and the high luminosity band. One reason for this could be because of the radiative wind. So maybe in the high accretion state, there is more wind, more radiative wind, which has pushed out particles, and so the X-rays are now have to go through these particles, and so the column density is higher in the high accretion state. We also see for both of the sources A and B, the inner disk temperature value increases to within standard error. So this does suggest there is a change in accretion state. However, it is only two recurrent sources. So from these two recurrent sources, we cannot draw statistically significant conclusions. However, it does suggest a change in accretion state. What are the conclusions to this project? There is some suggestion that the physical state of accretion in ULX change as the Eddington limit is met and approached. This is due to the difference in various parameters for the recurrent sources and also the difference in distribution of the inner disk temperature values between the low and the high luminosity band. However, we have no definite conclusion. We just have a suggestion to a change. So we need to do further studies to be more specific on what the change is. Suggestions for further studies could be to use more complicated models with higher quality data. The problem was that we used relatively low quality data. There exists higher quality data. With the low quality data, often a single component model was sufficient. And so when we modeled it with a 2-component model, it gave us strange values because the extra component was unnecessary. So a future study could be using higher quality data and using more complicated models to really pin down the change. We could also take sources with accurately known black hole masses which have observations in both luminosity bands. The problem in this study, we didn't know the black hole mass. We had to assume it was a 10 stellar mass black hole. So there could be cases where there is a more massive black hole in the higher luminosity band and a lower mass black hole in the lower luminosity band, and the one in the high band is actually accreting at a lower rate, which is not what we want. This is why we had to use 40 to 50 sources in each band. However, if we use accurately known black hole masses, the only thing that will be changing between bands will be the accretion rate. And finally, we could include a higher energy band to ensure that we include sources accreting above the Eddington limit. Maybe in the high energy band that we looked at in the project, maybe it was sub-Eddington accretion onto a stellar mass black hole of 20 or 30 or 40 solar masses. However, if we look at a third energy band above the energy bands that we looked at, we could be fairly certain we were definitely including super Eddington accretion. So I'll end my talk there. If anybody has any questions, feel free. You can ask me in Spanish, because I speak some Spanish, and I will probably answer in English. Thank you.